two quick examples of using the law of cosines. Other videos will be about recapping how we got it. SAS is the most basic situation. Let me switch to a better color. We've got a triangle, and we know two sides. Let's call this A, and let's say that's 14. Let's call this B. Let's say that's known to be 6. And let's say this side is C. That's the unknown, which we want to find. That's why I dotted it in. And big C, the angle opposite that, let's say that is 51 degrees. And the way I like to think about this is we have got two sticks, so fixed length, and then there's a hinge, and they can go back and forth. And then I set the hinge to be a certain angle, and these guys, the ends of the sticks, are connected by rubber band. And I want to know how long is the rubber band for a certain two sticks and a certain angle between them. Okay, this is just a nice way to visualize it. Well, here's the formula we came up with. We came up with a kind of like a 3 or 4 stage procedure, but then we distilled it down to a simple formula, a relatively simple formula, that's just Pythagoras plus some extra stuff with cosines, and that's the law of cosines. Okay, so that's just plug and chug, so we can now plug that in. I'm going to plug it in over here. There's the scratch work. So c squared is a squared plus b squared minus 2ab cosine c. Just plug in the 14 and the 6 and the 51 degrees. You get a number. Just remember that's c squared, not c. Take the square root. We get a number. Okay, let's see if it's reasonable. 11 and a quarter. Let's go back to the picture. 11 and a quarter, or 11.2 something. Yeah, it seems about reasonable. It seems like it's probably less than the 14, but definitely less than 20, which would be if you opened up the hinge and stretched the rubber band as much as it would possibly go. So that's one example. Very direct plug and chug. Only slightly more complicated, just because it's not exactly how we derived it, is an SSS situation. Let me draw an obtuse situation maybe. How about 10 and 5 and 13 are given. Let's call that C, that's A, and that's B. So I'm given all three sides of a triangle. We know from geometry there's an SSS theorem which says that that's enough information to determine a triangle. And I want to say let's get angle big C. We could get on any one of the three angles, but I'm just going to focus on big C. So is this going to help us? Let's see. We have an equation that talks about the three side lengths. Those are known. Oh, we're definitely going to be able to find cosine C, and then hopefully we'll be able to find the actual angle C. So let's work that out nicely. So here we've got, again, the law of cosines. But now we know all the distances. So we have 13 squared equals 10 squared plus 5 squared minus 2 times 10 times 5 times cosine C. Okay. So I'm going to bring the cosine over and bring the 13 squared over. So we're going to get, let's see, that's 100 cosine C, oops, equals 100 plus 25 minus 169 equals minus, so 125 minus 44. And so cosine C equals minus 44 over 100. Oh, conveniently enough, it's really easy to put into decimal. So it's negative. Does that make sense? Now remember, where does cosine get negative? It's exactly when the angle is bigger than 90 degrees. And so this picture does make sense. It really is an obtuse triangle. And if we take the inverse cosine of minus 0.44, we should totally get the right answer. So this is another good example of where you have to use an inverse trig function. Oops, that's the wrong thing. Now, here's what you would get if your calculator was in radians. Okay. Now you guys have the ability to just go ahead and do this calculation in degree mode. So you won't have to do this step if you put it in degree mode to start. I'm actually just going to convert it by hand to degrees out of radians. And it looks like 116.1 degrees. Okay. So that's going to be, in this picture, this angle is about 116.1 degrees. So I overestimated how big that angle is, it looks like, in my picture. But that's the general idea. It's definitely an obtuse angle.